So in the previous lecture, we have talked about the a function f which is continuous everywhere, but differentiable nowhere. We have constructed the function that there exists a function f which is continuous but differentiable nowhere. In this lecture, we are discussing regarding a term by term integration of the series. That means can be interchanged. So suppose there is a integration from a to b, summation k running from 0 to infinity, fkx dx is same as running from k 0 to infinity a to b fkx dx. So given that this each of this fk are Riemann integrable function, so can we interchange this two sign? That is, can we interchange the integration sign and the summation sign? Also, one can ask the question is Fn is a sequence of Riemann integrable function, and the set of all Riemann integrable function can be denoted as RAB, which implies whether it will imply that f is belongs to Riemann integrable. That means if Fn is converged to f, then can we say that if each Fn's are Riemann integrable, then f is also Riemann integrable? That means is this convergence is preserves the integrability. So the answer to this question is no for the pointwise convergence, that we have already discussed that example for that. Let us recall what was the example which we have discussed in one of the previous video. We have discussed that the Fn, if you define like limit of cos m factorial pi x power 2n as n tends to infinity for any x is in R, then we have proved that this Fn is a set of, it belongs to set of all Riemann integrable function over R, but the limit function, whatever the limit function we have proved that this Fn is converged to f, where this f is the function 1 if it is belongs to R minus q and 0 if it is belongs to q. And we know that this limit function is not Riemann integrable. So this does not belongs to RAB or R infinity, if we can consider as any interval. So this is the theorem which we have, or this is the example which we have discussed in one of the previous lectures. That means we can have a Riemann integrable function, its limit will not be Riemann integrable under the pointwise convergence. So if you want that limit function is also a pointwise convergence, then you have to go for further convergence, and which is known as a uniform convergence. And with regards to that, we have a next result which tells you that limit function is also Riemann integrable under the uniform convergence. So let Fn be a sequence of Riemann integrable functions on closed interval AB converging uniformly to the function f, then prove that f is Riemann integrable. And you can interchange the limit and the integration sign. That means limit of n tends to infinity, integration from a to b, fn x dx is same as integration from a to b, a limit of n tends to infinity, fn x dx. So you can interchange this limit and the integration, and this quantity is exactly same as integration from a to b, fx dx. So ultimately we have to prove this thing, that under the uniform convergence, the integrability, Riemann integrability is preserved. So without loss of generality, we can assume that this function, each fn's are real value. If not, we can separately doing the case which we are doing here for complex, real parts and imaginary part. If the it is complex value function. So without loss of generality, assume that fn to be real value. So if not, we can done. If not, we can done for real and imaginary part separately. The same procedure. So to do this or to discuss this, let us consider this epsilon n as a supremum of mode of fn of x minus fx, as x is belongs to closed interval AB. If I call this is the statement 1. Since this epsilon is supremum, we can say that for any x, fn x minus fx is less than or equal to epsilon 10 for every x belongs to AB. So by the property of this modulus, we can say that this is fn x or minus epsilon 10 is less than or equal to fn x minus fx. This I can write down minus fn plus fx is less than or equal to epsilon 10. So this is nothing but if I add both sides by fn x, then it is fn x minus epsilon 10 less than or equal to fx less than or equal to epsilon n plus fn x. If I call it, this is as star, and then I will take the integration both sides, integration from a to b. So therefore, this will be the integration from a to b. Fn x minus epsilon n dx is less than or equal to integration from a to b fx dx less than or equal to integration from a to b epsilon n plus fn x dx. But yeah, here I have made one mistake, that I don't know whether this function f is Riemann integrable or not. So what we cannot write this is integration from a to b. When we can say that the function is Riemann integrable if the lower integral and will be same as the upper integral. But obviously the lower integral is less than or equal to upper integral, that we can write. Ultimately, our objective is to prove that these two things are same. So from this, what we can say, therefore, the upper integral is always bigger. So that's why we can say that this is a less than or equal to b fx dx minus integration a to b. This is lower integral fx dx is less than or equal to integration from a to b fn x plus epsilon n dx minus integration from a to b fn x minus epsilon n dx, and this is always greater than or equal to 0. So this side we can observe that this is integration from a to b fn x plus epsilon minus fn x plus epsilon n dx. So this will simplify it as this fn x is cancelled out. This is 2 times epsilon n. Epsilon n is independent from x, so this is integration from a to b dx. So this is 2 times epsilon n b minus a. So finally, what we get is this quantity, that is 0 less than or equal to integration from a to b, upper integration from a to b fx dx minus lower integral from a to b fx dx is less than or equal to 2 times epsilon n b minus a. And given that this fn converges to f uniformly, given that fn converges to f uniformly as n tends to infinity, so therefore this epsilon n will tends to 0 as n tends to infinity. This is due to the uniform convergence. So if I take the limit in this, let's say this is equation 2 or inequality 2. So if I take the limit n tends to infinity in this inequality 2, therefore from 2 we get 0 less than or equal to limit of n tends to infinity integration from a to b fx dx minus integration from lower integral from fx dx, that is less than or equal to 2 into b minus a is constant from independent of n, and this epsilon n is there, and this will be tends to 0 due to this statement. So this is by sandwich theorem we can say that, and this is independent of this quantity is independent of n. So therefore we can say that this a to b lower integral is same as upper integral due to the sandwich theorem. And since these are the same, we can say that f is Riemann integrable because lower integral is same as upper integral. So therefore f is belongs to Rn. Now first task is proof. The first task is to show that this f is Riemann integrable. The second task is to prove this limit and the integration sign can be interchanged. So I will use the star inequality again. So from star, we have, so let us write down what is the star here, that is fn x epsilon n less than or equal to fx less than or equal to fn x plus epsilon n. Now we'll take this integration both sides. So this will gives you integration from a to b. So from star we have fn x minus epsilon less than or equal to fx less than or equal to fn x plus epsilon. Now if we take the integration from a to b, fn x minus epsilon n dx less than or equal to a to b fx dx. Now we know that f is integrable, so I can write down integration from a to b. Otherwise we don't know. and which we have proved actually is fx is differentiable, integrable. Now this epsilon is independent of x, so that's why this we can write down this is as integration from a to b fn x dx minus epsilon and b minus a less than or equal to a to b fx dx less than or equal to a to b fn x dx plus epsilon and b minus a. So as we have done earlier that mode of x minus a is less than epsilon, then we know that it is a minus epsilon less than x less than a plus epsilon. The same concept is here. This is your a, this is your epsilon, this is your x, this is your a, this is your epsilon. So this quantity is given to you. So we can write down this is equal to, or this is same as x, that is integration from a to b fx dx minus this integration from a to b fn x dx is less than or equal to epsilon and b minus a. And if you take the limit n tends to infinity, then what we actually proved is a limit n tends to infinity, this two distance, that means this is less than or equal to 0. And this I can write down same as integration from a to b fn x minus fx dx. This tends to 0 as n tends to infinity, because this will tends to 0 as n tends to infinity, and this is already greater than or equal to 0. So by sandwich theorem we can say that this is equal, or this will tends to 0. So I can say that a limit of n tends to infinity integration from a to b fn x dx will be same as integration from a to b fx dx. But what is fx? Fx is a limit function of fn, that is this. So hence we have proved that under the uniform convergence you can interchange the limit and the integration sign. The corollary of this results we state in this manner. That means let fn be a sequence of continuous functions on AB, and suppose that fn converges to f uniformly on AB, then we can have f is if then we can say that limit n tends to infinity a to b fn x dx is same as limit integration from a to b limit n tends to infinity fn x dx. So ultimately the corollary of this results is changing a function which are Riemann integrable. Instead of that we have taken a continuous function, and we know that if f is Riemann integrable, we know that f is continuous, which implies f is Riemann integrable. So every continuous function we know that it is Riemann integrable. So that's why according to the previous result f is Riemann integrable, and so we can interchange the limit and the integration sign. And the reason for this result is just you can state one line, that is CAB always a subset of RAB. So this class of Riemann integrable function is a bigger class than the CAB, that is set of all continuous functions. So that's why there is no need to prove this theorem separately, which we already did it. Now the main result that we were talking about, that is the term by term integration This result is known as a term by term integration. That means we can interchange the integration and the summation sign. So let Fn belongs to Rab, that is set of all Riemann integrable function, and let the series summation n running from 0 to infinity in Fnx converge uniformly to the sum function f on AB. So this series is converged to f uniformly. Then prove that f is Riemann integrable on AB, and the integration summation n running from 0 to infinity Fnx dx will be same as summation n running from 0 to infinity integration from a to b Fnx dx. That means you can interchange the summation and the integration sign. So let us try to prove this statement. And obviously to prove this statement, we have to use the previous result which we have did. Because the convergence of series is related to convergence of sequence. So here first given that this Fn converges to F uniformly. So given that series n running from 0 to infinity Fn converge to F uniform on closed interval area. What does that mean? Therefore, the partial sum summation k running from 0 to n Fk is converged uniformly to F. But we know that if F is Riemann integrable, if G is Riemann integrable, then will imply that F plus G is also Riemann integrable. That means the sum of two Riemann integrable function is Riemann integrable. That we know. Here each Fn's are Riemann integrable. So in particular this summation of F, this partial sum Sn is also Riemann integrable. So I will call it this is as Sn. Since each Fn's are Riemann integrable, the partial sum, that is sum of the Riemann integrable function, the Sn is each Sn is also Riemann integrable. So what is the previous result says? The previous result says that if you have Fn converges to F uniformly and each Fn's are Riemann integrable, then F, the limit function, is also Riemann integrable. So here is we have a same thing. Sn converges to F uniformly and Sn is a Riemann integrable. So automatically this F is also Riemann integrable. So we can say therefore by previous result, F is belongs to Rab, or I can say F is a Riemann integral. And we can say that a limit n tends to infinity, integration from a to b Snx dx will be same as integration from a to b limit of n tends to infinity Snx dx. This is due to the previous results we can write. Now what is Sna? We know that the Sn is the partial sum, so let us substitute that value. So it says that limit summation n running from k running from 0 to n fn x dx, which is same as integration from a to b limit n tends to infinity Sn x dx. But what is Sn x dx? We should substitute that value here. That Sn x is k running from 0 to n fn x. But you will take the limit here, then this will be limit a to integration from a to b a running from 0 to infinity fn x dx. And on this side, this is the finite sum. Due to this result, that integration a to b f plus g dx is equal to integration from a to b f plus integration from a to b g. So due to this result, and this is the finite sum, this quantity is a finite sum, that is k running from 0 to n. In that, we'll interchange this two, so that for this is limit n tends to infinity summation k running from 0 to n integration from a to b fn x dx. We can have. Now we'll take the limit here. Therefore, this is summation k running from 0 to infinity integration from a to b fn x dx is equal to integration from a to b summation k running from 0 to infinity fn x dx. And this completes the proof of the term by term integration. See, in this theorem we have proved this thing, that under the uniform convergence we can able to interchange the limit and the integration and the summation and the integration, infinite summation and the integration. But it is not necessary condition. It is sufficient, but it is not necessary. That means it's not that under the pointwise convergence it should not happen. Okay. So I can write this is an example in this manner, so that the uniform convergence condition for the change of the order of limit and integration is sufficient but not necessary condition. So it is sufficient condition but not necessary one. Okay. So for that I need to give or construct an example that under the pointwise convergence this may happen. So let us have the same statement in another way. Consider fn x is equal to integration from this 1 upon 1 plus nx if your x is belongs to closed interval 0 1. Then so that limit n tends to infinity integration from 0 to 1 fn x dx is same as this. Even if the convergence of fn is not uniform. That means under the pointwise conversion this is true. So it means that the condition is sufficient but not necessary. So this condition is not necessary to having the convergence, pointwise convergence, the uniform convergence. For interchanging the order of integration and the limit or integration and the summation. So let's give the solution for this. Here the function fn is given you as 1 upon 1 plus nx. This is the function your x is belongs to 0, 1. And if I take the limit n tends to infinity, fn x will gives you limit n tends to infinity 1 upon 1 plus nx. That I can write down limit n tends to infinity 1 upon n upon 1 upon n plus x. So this is 0 upon x. If x is not equal to 0, then this will be the 0 answer. So here x is not equal to 0, then fn converts to 0, but in this interval 0 is there. So that's why I need to calculate what is fn at 0. Fn at 0 is 1 upon 1 plus 0, so that will be 1. Fn at 0 is 1. So ultimately what we can say is fn x is converse to fx, where your f is 1 if x is equal to 0. So if fn x is converse to 1 actually, and 0 if it is between this. But this will tells you that this convergence is pointwise, never be a uniform, because the limit function is not continuous function at 0. So thus we can say that here f is discontinuous at x is equal to 0, and therefore fn does not converged uniformly to f. That we conclude. Ultimately we have to show that this limit and integration is same. So for that I may start down with the integration limit fn x dx as n tends to infinity. So this is 0 to 1, and you know that the limit of this function is either 0 or 1, and over the integration from 0 to 1, so this is 0 dx will gives you 0. So on this one side it is and the answer 0. Now let us calculate the integration from a to b fn x dx as n tends to infinity. So that is limit is there, integration from a to b 1 upon 1 plus nx dx as n tends to infinity. That is limit n tends to infinity, but here the integration of 1 upon 1 plus nx is log 1 plus nx upon n. A limit is from 0 to 1. That is the limit, or there is the interval is given as n tends to infinity. So when I substitute 1 here, then it is log 1 plus n upon n, minus when I substitute 0 here, log 1 upon n as n tends to infinity. But log 1 is 0, so ultimately this will convert to limit n tends to infinity log 1 plus n upon n. And you just note that this is infinity upon infinity form by taking the limit n tends to infinity. This is numerator is infinity, denominator is also infinity. So you have to take the integration by parts here, or sorry, you have to take the L'Hospital rule, because it is indeterminate forms. That is n limit coming from this. This is 1 upon 1 plus n upon 1. And this will converge to 0 as n tends to infinity. So finally this limit or this answer is 0 on this side, and the other side is also 0. So hence we can say that integration from a to b, or I can say 0 to 1 fx dx, and if I take the limit n tends to infinity, limit of this is same as integration from a to b limit n tends to infinity fn x dx. And this conclude that the integration and the summation sign, sorry, integration and the limit sign You can interchange even if, but not always, under the pointwise convergence. So ultimately, the uniform convergence is a sufficient condition, but not uniform or not necessary condition. In the next lecture, we'll talk about the term by term differentiation of the series. That means if fn is differentiable, so here I have denoted this DAB is a set of all differentiable function over the open interval A. That is represented as D of AB. Well, it implies that f is DAB, f is belongs to DAB under the pointwise conversion, under the uniform conversion. Will it is true? Or can we interchange the derivative sign and the summation sign? So can we do this in general for infinite sum? So these are the few questions you have. Try to find out what is the answer for this, and we'll discuss the answer for this questions in the next lecture. If you have any question, you can ask.